In this tutorial, we will learn the fundamental mathematics that are useful to understand group theory. We will cover orthogonality, vector space, representations, vectors, tensor products, matrix multiplication and the trace of matrix. Additionally, we will try to give a glimpse of their direct use in group theory. First, let's understand what orthogonality and vector space are. A vector space is a collection of objects that can be combined linearly, like vectors. For example, spatial vectors x, y, and z, wave functions psi1 and psi2, and these are a few examples of vector space. Now, coming to the orthogonal vectors. Two vectors are said to be orthogonal if their dot product is 0. Suppose we have two vectors a and b. If they are perpendicular to each other, then their dot product will be a dot b cos 90, which will be equal to 0. When two vectors are orthogonal, they are said to be independent of each other. But not all independent vectors are orthogonal. Here, the independence means one vector contains some information that cannot be generated from the other. One vector cannot be expressed just by scaling the other. Like a cannot be expressed as a scalar multiplication of b. Suppose I have two vectors such as 1, 2 and 2, 4. These two vectors are not independent vectors because the second vector is a result of scalar multiplication of the first vector. So, both vectors point in exactly the same direction. But if we have 0, 1 and 1, 0, then they are independent vectors. Because they point in a different direction and they cannot be expressed in terms of each other. But are 1, 0 and 1, 1 independent. Here 1, 0 cannot be mapped into 1, 1 by scalar multiplication. So, yes, they are called independent vectors. But they are not orthogonal vectors. As stated earlier, not all independent vectors are orthogonal. If you take the dot product of these two vectors, then it will not be 0. So, orthogonal vectors are a special kind of independent vector with 0 overlap. That naturally raises the question: why introduce a special term, orthogonal, if independence already exists? Because orthogonality gives something much stronger and mathematically cleaner. For example, the vectors 1, 0 and 1, 1 are independent as neither vector is a scalar multiple of the other. However, they are not orthogonal because the second vector has a component along the direction of the first vector. Orthogonality means completely separated. Examples 0, 1 and 1, 0. Here, we can say one vector is purely x and another is purely y. They do not overlap at all. Orthogonal vectors make mathematics incredibly simple. They do not interfere with each other. Orthogonality is the backbone of irreducible representations. Representations behave like vectors in symmetry space. Now what does it mean? Let's understand this using the three layers. Layer 1. Functions such as px, py, and pz orbitals. These are the real vectors in the real physical space. Then, Layer 2. Matrices, which are operators acting on those vectors and transform them. And finally Layer 3. That is characters of representations, which are vectors in class function space. When we say representations form a vector space, we are mainly talking about Layer 3. A representation assigns a matrix to every symmetry operation. and the dimension of the matrix will depend on the number of bases. If your basis has one function, then matrices are one-dimensional. For two functions, matrices are two-dimensional. For three functions, it is three-dimensional. But in representations, whether it is reducible or irreducible, we do not use the full matrix here. Instead, we compress each matrix to a number, that is the trace of the matrix. This is the character that carries the information of the matrix. So a representation, both reducible and irreducible, contains the characters and is really a set of matrices. It is important to mention that functions are the real physical space. It has a real physical meaning. But representations are abstract form. And each representation becomes a list of numbers. And that list behaves like a vector. We call them vectors because they follow the mathematics behind the vector. Like, they can be linearly added to give a new vector, can be multiplied by a scalar, and can be decomposed to form new vectors, as from reducible to irreducible forms. For example, a reducible representation can be represented as tau is equal to character of E, character of C to character of C3 and so on. This is a vector space. Suppose a point group has 4 classes. So, whether it is reducible or irreducible representation, it will have 4 characters as shown here. To this representation, we can say it is a 4-dimensional vector. Now, here, we should not be confused with the dimension of the functions, which is the character of identity element that we have explained earlier with the dimension of the representation. The dimension of any representation is equal to the number of class present in that point group. To simplify this, let's take the example of C to V. Here, irreducible representation, say A1, will look like this. And B1 will look like this. So, these irreducible representations have 4-dimensional vector space. In molecular symmetry, the irreducible vectors are considered as the basis vectors. A basis vector is one set of independent vector needed to build every other vector in a space. And a basis vector cannot be further reduced, like the irreducible representations. Now, we have another 3-layer picture. Layer 1 is the individual representation, which is called a vector space. That can be reducible or irreducible representation. Layer 2 is a direct sum of irreducible representation, builds larger spaces that we called reducible representations. And layer 3, a larger vector space, such as reducible representation can be reduced to smaller vector space that we will call basis vector or irreducible representation. So, a reducible representation is the larger vector space. And it can contain multiple irreducible representations which are the basis vectors. This can be represented as tau is equal to tau1 plus tau2 plus tau3. Addition of representations tells us which symmetries are present in a reducible representation. And reduction formula decomposes a reducible representation into irreducible ones. Now, multiplication helps us to analyze the interactions between functions, especially when 3 components are involved, which are the initial state, operator, and the final state. If function A transforms as an irreducible set called tau1, and function B transforms as tau2, then if we want to see under which possible ways these two functions can interact, for that we need a multiplication. Here, it is important to mention that in group theory, When we say multiplication of character, by this, we mean it is a tensor product, not a normal matrix multiplication. Because, in normal matrix multiplication, when we say M2 multiplied with M1, that means M2 acts after M1. And then we get the final transformation. Here, we will have no information about what the interaction between the two different set of functions yields. But in tensor product, we can investigate each possible interaction between the character of the matrix of an operation. So multiplication of representations tells us the possible symmetry channels through which different functions interact. If under operation, let's say C2 rotation, one function, A, from irreducible representation tau1, transforms like the character chi1 of C2, and another function B, from tau2, transforms like chi2 of C2, where chi1 is the irreducible character of function A for C2 and chi2 is the irreducible character of function B for C2. Then, the all possible interaction between A and B can be described by the tensor product of chi1 and chi2. Let's go to the matrix level. But we need to separate two cases carefully. One is one-dimensional irreducible representations and another one is multidimensional irreducible representations. We already know, for a symmetry operation, let's say R, each irreducible representation assigns a matrix, say M, R. The character is the trace of the matrix. When the irreducible representation is one-dimensional, then for all symmetry operations, the matrix will have only one element, that is a 1-by-1 matrix. Here the trace is the number itself. So, when we multiply character of operations of two functions, we can multiply directly. That is why, in C2V point group, which contains only one-dimensional irreducible representations, we simply multiply rows. It requires no matrix multiplication complexity. But, the scenario changes when we move for multidimensional representations such as E and T. Now, suppose we are in a group like C3V or D3H, where there are two-dimensional irreducible representations. Now things change slightly. If, for a symmetry operation R, a set of function A and B transform under irreducible representation tau1 with matrix M1, R and function C and D transform under irreducible representation tau2 with matrix M2, R. Then, the possible symmetry channels through which A and B will interact with C and D can be found out under the tensor product of M1 and M2 instead matrix multiplication.
The trace of the tensor product of the two matrix will always equal when we multiply the character chi1 with chi2.
In normal matrix multiplication, if M1 and M2 are a 2-by-2 matrix, then their multiplication will also produce a 2-by-2 matrix. The dimensions stay the same. But in tensor product, if M1 and M2 are 2-by-2 matrix, their product will generate a 4-by-4 matrix. Here, the dimensions multiply. That is the key idea. Again, the question is, why we don't follow normal matrix multiplication here? If you multiply two matrices, you are describing it as first, apply transformation M1. Then, apply transformation M2. It represents sequential action on the same vector space. Normal matrix multiplication assumes both matrices act on the same space. But, when we multiply irreducible representations in group theory, we are not applying one symmetry operation after another. We are combining two independent vector spaces. Here our target is different. For example, if one function lives in space tau1, another function lives in space tau2, their product lives in a new space, which is a tensor product of tau1 and tau2. That is a completely different space. So we are not composing transformations. We are constructing a representation on a combined space. That requires tensor product. Now, let's understand how matrix multiplication is different from tensor multiplication. Let's see how tensor creates a difference here. Assume we have two irreducible representations, tau1 and tau2, and both are two-dimensional representations. Which means each contains two functions, such as a and b in tau1 and c and d in tau2 that mix under a symmetry operation. Let's say an operation C2. The character of the irreducible representation for tau1 is chi1 and for tau2 is chi2. Since character is the trace of the matrix, let's have two matrix for both the character M1 and M2. Now, we will see what will happen when we are multiplying the matrix. For matrix M1, the trace is a plus D, which is chi1. Similarly for matrix 2, the trace is E plus H, that is chi2. Now, if we perform simple matrix multiplication, then we will have the new 2 by 2 matrix. And now for this matrix the trace will be AE plus BG plus CF plus DH. This trace is not equal to if we multiply chi1 with chi2. Now let's see what happens when we have a tensor product. In tensor multiplication, each element of matrix M1 is multiplied with the matrix M2, which generates a new 4 by 4 matrix as shown here. Now, the trace of the matrix will be AE plus AH plus DE plus DH. This will be same if we multiply chi1 with chi2. And the overall 4 by 4 matrix contains all possible interactions between the 2 by 2 matrices. Again, to determine the tensor product of two matrix, we don't need to use the whole matrix. We can get the same information if we simply multiply the character or trace of the individual matrices. This becomes very useful in group theory, because by multiplying characters of each irreducible representations, we can able to get the information about all possible interaction. In next, a transformation matrix is simply a matrix that tells us how a function or a set of functions changes when we apply a symmetry operation. When a symmetry operation acts on a set of functions, it transforms them into linear combinations of each other. Suppose we have a set that consists of some basis functions. For example, take the three functions x, y, z. Now apply a symmetry operation, say a C4 rotation about the z-axis, and see how these function changes. It is important to note that we have included the sign of the axis in our basis function. Here we are studying the transformation of a group containing three different functions. Mathematically, we can represent the operation using a matrix form. Let's say, after the C4 operation, the new set is x prime, y prime and z prime. Then how the new set is related with the x, y, z can be determined by a suitable matrix. If we observe the C4 operation on x, y, z, then we will find x is moved to the y becomes minus x and z remains unchanged. Here, by observing the changes, we can design a matrix which can explain how individual x, y, and z transforms. In this case, C4 acts on x, y, z to form x prime, y prime and z prime, which is y minus x, z. Here, the C4 matrix can be easily evaluated by using simple matrix multiplication. The C4 matrix for x, y, z is this. The size of the matrix depends on the number of functions that we observe. It can be one-dimensional or multidimensional. If we consider only one function, let's say x, then the matrix will have only one element. We will call it one-dimensional matrix. For example, if x is a function which is closed under operation, let's say O, and it transforms it into ax after the operation, then the matrix will contain only one element, that is A. If we have two functions, such as x and y, then the matrix associated with the symmetry element will be two-dimensional. Here we are observing the changes for x and y. If after the symmetry operation, x becomes ax plus by, y becomes cx plus dy, then the transformation matrix will look like this. Here there are two rows and two columns. Here, it is important to note that among all the elements of a multidimensional matrix like A, B, C, and D, A and D carry significant information. These are called the diagonal elements. In this example, if we say after the symmetry operation, the new x, which is x prime, is a linear combination of x and y, such as ax plus by. Here, if we want to know what is the contribution of x in this new transformation x prime, then the answer will be A. Although, B also contributes to the new function, x prime, but it carries the information for y. Similarly, for y prime, which is cx plus dy, only D tells the contribution of y in y prime. So if we consider the diagonal elements of a matrix, we can say how the original function is contributing to the new function. This is the example of two-dimensional matrix. Similarly, if we increase the number of functions, the dimension of matrix will increase. For example, if we have 5 different functions, then we will have a 5-dimensional matrix with 5 rows and 5 columns. And all the diagonal elements will be used to understand the contribution of a particular function in its new function. Here, the sum of the diagonal elements of the matrix is called the trace of the matrix. This is what we call the character of a particular symmetry element for a particular set of functions. Now coming to a real example, suppose we want to analyze the transformation of 5D orbitals under a symmetry operation, let's say C4 axis. Here we have 5 functions. So the matrix of C4 must be 5-dimensional, that means 5 rows and 5 columns. First, we will observe physically how the functions change in the presence of the C4 axis. And based on their change, we will fill the character of the 5-dimensional matrix with the C4 operation along the z-axis. xy becomes minus xy. yz becomes minus xz. xz becomes yz. x square minus y square becomes minus x square minus y square. And z square remains the same z square. The matrix will now look like this. If we multiply the functions by this matrix, then we will get the new functions. Here if we look at the diagonal elements, in the first row, which is related to the first function xy, is minus 1. It indicates the function xy changes to xy with a change in sign. That also indicates xy contributes fully in the new function minus xy. In the second row, which is associated with the second function yz, the diagonal element is 0. It is because the corresponding function, yz, is completely transformed into minus xz. So it has zero contribution in the new function. Similarly, for xz it is 0. And for x square minus y square it is minus 1. And since z square remains as z square, after the operation, the character of the diagonal element is 1. And here it is fully contributing to the new function. Here the trace of the matrix is minus 1. This is the reducible character of the C4 axis for the 5D orbitals.